Alright, hello everyone, it's March the 9th. Alright, let's do this. Hopefully we did better than yesterday and have some time to finish the other one. Alright, linked list random node. Given a singly linked list, return a random node's value from the linked list. Each node must have the same probability of being chosen. Include the solution class. Initialize the object with a head of a single linked list. Random, choose a node randomly from the list and return its value. The nodes of the list should be equally likely to be chosen. Okay. The number of nodes is 10 to the 4th, so I mean definitely we can just get everything out and then randomly choose one. So if you use it, if you got really lazy, it's very easy to solve. However, let's try this. What if the linked list is extremely large and its length is unknown to you? Could you solve this sufficient without using extra space? Let's try that approach without extra space. Well, it didn't say that we cannot make changes to the list, right? So what was the method to randomly select something? Something like put something to the end of the list, something like that. But I forgot how that is. Let's see. Put something at the end. Yeah, that's what I remember, right? If you want a random, you put it at the end. Reservoir. It's not put at the end, but let's see the reservoir. What's it called? Reservoir random sorting. What's the name? Reservoir sampling. Okay, reservoir sampling. Yep. Random choosing k samples from a list of n items, where n is a list and it is either very large or unknown number. Typically, n is large enough that the list doesn't fit into mainline memory for list search queries. A sample solution is to create an array of a reservoir of maximum size k. One by one, randomly select an item from. If the selected item is not previously selected, then put it in reservoir. Check if item is pre-selected, we need to search the item reservoir. The time complexity is OK squared. This can be costly if k is big. Also, this is not efficient if the input is in the. This is a simple solution. It can be solved in O(n) time. Solution also successful. Create an array of reservoir. Copy the first k items. Now, one by one, consider all items from k plus 1 to the nth. Generate a random number from 0 to I, where I is the index of the current item in stream. Let the generated random value be j. If j is in the range 0 to k minus 1, then we replace reservoir j with I. Oh, that's it. There's a proof. Maybe we can try to write the proof ourselves. I remember I did it in the past. So basically, as we go in, right? As we go in, for each one we pick a random number from 0 to I. Okay, so I'll pick a random number from 0 to I, and if it's in 0 to k minus 1, then we swap the value, which means for the current value, the probability of it being swapped in is right. So we'll have, this is 1 over I probability, which we pick one, and the probability of it is within k is probability of this choosing is inside. Is 1 over k, right? So the probability of swap in is 1 over k, and the probability of swapping out is, yeah, I forgot. What's the thing for n k item for stream I? For every stream item, we pick a random index. Pick is one of the first k we replace, so that means it's being selected. So it's 1 over. Probability that the last one is in wait, hold on. The probability that the last item is in final reservoir is the probability that one of the first k index is picked. Yes. If one of the first to get picked, so k over n, it's the probability of the last one, okay. So before the second last one is the probability of, pick one. So it's n minus 1, k over n minus 1. Right? And times, so probability of choosing this hold on. The probability that one of the first k index is picked in iteration for stream n minus 2. Because it's from time probability that the index picked in iteration is not same as index picked for stream n minus 2. So you don't swap out. Okay, so at position is n minus 2, right? So from 0 to n minus 2, what we need to do is the probability that it's been chosen, right? It's been chosen, which is n minus 2. It's been chosen, so the probability should be k divided by n minus 1, right? It's the probability at this position. And then the probability that the next one does not choose it, which means the next one with n, that position n minus 2 is not selected. So the probability is n minus 1 divided by n. So the probability is not chosen. So the result is k over n as well. And of course, here, there should be n minus 1. There should be n minus... Oh, the stream this. Okay, that's right. Yeah, so for each one, so for the next one should be k divided by n minus 2, and the next 2 does not choose it. So n minus 2 divided by n minus 1 times n minus 1 divided by n. It makes sense. Okay, the first k is every time you choose, you do not replace it, right? So the probability of that is k plus 1, right? you don't replace this, which is k divided by n. And then there's k plus 1. So we have k. Now we have the first one, have the second one. So among all these, we don't want to replace this. So if we don't replace this, that's k divided by k plus 1 times k plus 1 divided by k plus 2 times all the way down to the last one is going to be n minus 1 divided by n, and they all divide, so it's k over n. Ah, I see. Okay, then how can we use this for, oh yeah, we can use this. We can. Because we only return one value, right? So the size is just 1. The size is just 1. It doesn't really mean the size. It's just a pointer, right? Just a pointer. We point at this one, and when we get random, we roll a random, and then if it's the same, we return this one, right? Because we swapped. If it's not the same, it's not rolling, we return this one, and then we just keep going down. Yep. See, this is good. I mean, is it really useful? I'm not sure, but the point is not whether it's useful. The point is, the whole point, right, is that if a similar problem show up in real life, you know there's an algorithm called the reservoir sampling, and you know how it works. And that is the most important thing. Self.node, right? We need a node equals head. Do we even need index? All right, self.index, index style is 0. Okay, and then we need a value, right? Self.val equals head.val. I wonder if I need this. I don't think I need this. But as I go down, 10 to the 4 calls will be made. No, I do need head. I do need a head. Because we can just exhaust the whole thing, and then I have to start from the front again. Start from the front again. Do I reset index? Right? Yeah, you reset index. Okay, so we're gonna return random, so then we need to go I equals random, right? Random. So we can say random.rand int from 0 to self.index. Self.index plus equal 1. Hold a second. That's fine. That's fine. No, that's not fine. Because what if you only have 1? Alright, if you only have 1. So what I think is, if not self.node equals head, and Hold on. Let me think again. No, we can keep going. It's fine. It's totally fine. It's totally fine. We just keep looping through, and the index will just keep growing. Index keep growing. That is totally okay. That is actually not okay. Oh, it's fine. Index keeps growing. That's okay. Is that okay? Index keep growing. It's just like you're repeating this thing, right? You're repeating this thing. But if the index keep growing, right? And every time we try to see if 0 is selected. Right? We say if it's inside, then we will swap. But my length is only 0. Right? My length is only 0. It says it has to be from a random number from 0 to I. Right, if this j is inner, so in my case, if j is equal to 0, right? So if I keep going, the chance of it being 0 is smaller and smaller. Then we just never replace. We just never replace. Huh? Does that work? Does that work? We never replace? So imagine it keep growing, right? No, that's no, I think we have to reset. We have to reset. We have to reset. Okay, so we will move down to the next one, and then if it's bad, right, if it's none, then we will, what if it's none? Yeah, we move down and then it's none, so we exhaust the whole thing. Well, if we exhaust the whole thing, and then we move down one more time, because as we're going through, we can get a random, yeah, next time we move down, and then we find a random, next time here we find a random, and next time we go down, we don't, and we need to so here's what I think, okay? Here's what I think. If it's only one node, in my case, if it's only one node, then so what I said, if not self.node, which means no, we wouldn't do this. Self.node equals self.node plus a dot next, okay? Self.index plus equal 1. If not, then self.node, right, equals if not self.node, which means when we go to the end, if we go to the end, then we shall respawn to head on next, right? We respawn to head on next, and self.index equal to 1. Okay, that's what we do. Right, so now we are at the right position, and then we say if not self.node, then we just return self.value. But now self.node is nothing, then we're coming back up. We had the same problem. So we go to the next, and if we reset, We need to reset this to self-dot. Hold on. This is just... Hold on. What if I have 2? Okay, we do this, and then we can get it. Next one, you go this, then we do this, then we can get it. Yeah. So I think the problem, let's just say if not self.head.next. Right, we just always return self.val. Single node, but always. Otherwise, we do this, right? We move down, and if this, we will do this. Then we are at the correct position. And then we say I is equal to random from this, okay? And if I is equal to 0, basically just if this is equal to 0, right? Then we're gonna swap. Not swap, we're gonna replace, which just means we're gonna say self dot. Well, we don't even need the self dot val. We can just return, right? We can just return self.node.val, right? Self.node.val. And then we don't need this. This is not needed. We do need node, we do need head. And this is self.head.val. Okay, let's go through this one more time. If we have a single one, then we always do this, which is perfect. We have 2, then this one does not satisfy, and then we go here, node move to the next, index become 1, and this is don't do, and then we just do a random. If it's 0, we will return this. Else, oh, what if else? Dude, we do need a val. When they say self.val equals self.node.val, and then we shall return self.val, right? That's the replace. Yeah, now we replace it and return this. If it's now, we return the original. Right now, the next one, node move again. We do this again, and then we do it again, right? And now we do it. It's if this, Now we keep going, keep going, keep going, keep going, and once we hit to the end, this is the last one. Okay, the last one. The last one, this is false, right? So this is true because yeah, we had the last one. We redo, basically redo this, and then should we reset self.val as well? It's an interesting question. That is an interesting question. Yeah, what if you're... Yeah, you only have 3, right? And then we call it so many times. In this case, the first one time... First time I do this, second time call, and the third time, so like the third time we call will never get to the other value. That doesn't seem right to me. It doesn't seem right to me. And how do you do it? Once you hit the entire length, do we imagine it just go in cycles? We can imagine it go in cycles. But still, if we go in cycles, then they will not be equally distributed. And the thing is, it's really long, right? It's really large. Like in my case, the first call will never give you 3, which is not random. Huh. Yeah, it will never give you 3. Because it's the reservoir sampling is thinking about stream, right? So the value at the end has not been seen yet. But this one, it's already been seen. It's already there, right? It's already there. You can already see those. So I don't think random reservoir sampling doesn't seem to be the right way to do this. But this is like strongly hinted as reservoir sampling. No, reservoir sampling does have the equal probability, okay? Once you go to the end and you start again. You know what? I think this shall be right. It does have equal probability. I'm not sure. Let's see. Oh, head. Let's see. Let's do a lot more just to make sure. 1, 2, 3, 4, 5. One, 2, 3, 4, 5. Okay, maybe that is the way. Maybe that is the way. Let's give it a shot. No. They don't like it. They do not like it. I don't think it's random enough. It doesn't seem random to me. Look at this. Yep. It's not random enough. Which is true, right? It's true because as you start getting, it's harder and harder to random to 0. But my index also changes. My index also change. My index also change. Doesn't that already reset the whole thing? Yeah, I mean, basically, in this case, at the end, they just stay the same. This does not stay the same. Maybe we should not reset. But again, if we don't reset, if we do not reset, like imagine, right? Imagine you just repeat the thing many times, right? And then each one has the probability of, like, if it's, this is what, 5 values. If we do 2 rounds, so you just repeat it twice, right? You repeat it twice. Now everyone has the same chance of appearing, because that's 2 out of 20. So that's 2 out of 10, right? That's 1 out of 5, so it's the same. So now you're just increasing. So what I'm saying is, once you hit the end, you go back to the front. Okay? Once you hit the end, you go back to the front, and your index just keep growing. But your index keep growing. That's the thing. Your index keep growing. And the probability of them getting chosen is getting smaller and smaller. Like, they won't even change. They'll just stay the same value. Can reservoir sampling be used with n equal to 1? Yeah, it should be, if you can, right? You can do n equal to 1. There's no restriction on n equal to 1, but it doesn't feel right. I'm trying to do this as n equal to 1. This is not right. Because if you loop back, then after a certain amount of call, someone will have higher chance of getting picked than the others. The reservoir sampling only guaranteed everyone in the first go, everyone has the same chance of being picked. Oh, hold on. Reservoir sampling is you have to go through the entire thing and then you return the thing. It's not returning every single time. Oh my god, this is a wrong use of reservoir sampling. No, I realized reservoir sampling have to go through the entire thing. You don't just, yeah, you have to go through the entire thing and you return. Ah, that's not reservoir sampling, because we want Every call. Nah, that's not right. Then what do you do? Every call. That's bonkers. You can't just like every time you call, you go through the entire array. That's just stupid. I don't believe that's the solution. What was this? Then I think it's probably something like pushing to the end. But I don't remember how that scheme worked. That scheme is different. That scheme is randomly pick a value and then you have to remove that value. It's randomly pick one and put it to the end and then you pop it. That's different. Lord. Do you have a hint? It does say reservoir sampling. What the hell? How'd you do reservoir sampling on this? Oh man. You can't, right? You can't just every time just run through the whole thing. That would be 10 times 4 times 10 times 4, the whole runtime. It's gonna be ridiculous. Reservoir sampling guarantees at a certain time, right? Yeah, something will have higher chance to appear than the others. You have to go through the entire thing, then you can guarantee the return value, right? They all have equal chance of appearing in that. They all have equal chance to appear in that. Huh. No. Because that's extra space as well. I'm out of ideas. What did I use? I think that's reservoir sampling. No way. No way. You cannot be like this. This is literally what I was thinking, and I don't want to do it this way. Because I thought it's going to be so stupid. You have to go through the entire thing. How come this one is fast? It's not gonna be fast. Well, honestly, it's not fast. Oh man, this is ridiculous. This is ridiculous. This is ridiculous. They basically just said, right? Val. Dot next. While node. If random dot rand int 0 to I. Oh, I need I. Equal to 0. Not equal to 1. Is equal to 0. Val equal to node dot val. Right, I plus equal 1. And then we return val. So usually every time you go through the entire thing. That's stupid. That is as stupid as they can be. Alright, that's as stupid as they can be. No, that's not node.val, it's self.head. And no equals. This is stupid. All right. Okay, this is reservoir sampling, and it uses O1 space, but it can be very, very slow if the linked list is long. Right, so the runtime is ON runtime. We thought about this, but we just didn't follow up. Because it was incredulous to me. It's like, how could this work? Right? How could this work? It's just stupid, right? It's just stupid. On the other hand, I'd rather just do it the regular way, you know? No, that's 1. That's 2. I will just do self dot list equals this while head self dot list dot append head dot val head equals head dot next. And then for this we just return self dot list random dot choice. Is that choice? Not sure. Not 100% sure. Did choice choose 1 or? Yeah, choice choose 1. Alright, use ON space to make the call O1 in time. But it's fine. We went through reservoir sampling, so it's not too bad, okay? It's not too bad. Well, we did waste a lot of time. That's something I don't like. Waste a lot of time. I was having intention to go for that, but Lord, we still haven't got a time to do this. And I mean, these problems just constantly giving me issues. Alright, I don't want to do. Let's just cut it here. I'll see you guys tomorrow. Adios.